All right, so we before we jump into today's topic, I do have a few announcements. The first is those worksheets that were handed out Wednesday, they're due Sunday. So if you need a little extra time to work on them, you have that. The next thing is the one with the ball being dropped and the boy on the table. I did post something in the discussion boards and I solved it. So if you need those are there. Two things that kind of came, well, one thing is, in the worksheet on the drop part, initially first question was about like, what is the speed of the ball before it hits the ground? And a lot of people have like a negative number there. Not remembering that speed means make a positive when you put that answer in. So I did go through and give people credit for that negative value, if you had that velocity negative. The next thing in that is the ball hits the ground and stops. It doesn't hit, bounce, and then come back down. It just hits and stops. That 10 centimeters is how far the ball kind of goes down before stop. Okay? And that also leads to the acceleration, force, and impulse all have to be up if the ball is coming down to stop it, which means those answers should be positive. A lot of people had all three of those negatives, which means the ball wouldn't stop. Right? You had the signs back. So just pay attention to that. But like I said, there's a video posted. Now I did change the wording in the question. If you open it again, it now does read, what is the velocity of the ball before it reaches the ground? So if you still have to do that, pay attention. One other thing to note, with the boy on the table, common mistake was people were putting the torques in wrong into the sum of their torques. Not the values or anything like that, but the sign. So one way to think about it is, wherever your pivot is, if your pivot was, let's say, where my X is, you can think about drawing like a little quadrant set there. Now, to think about it this way is any force that's in this quadrant on your lever arm is a positive torque. If the force is in this quadrant, it's a negative torque. So if you have forces that are pulling this way, that's a positive torque about that pivot. If you have a force in this quadrant, it's a negative torque. If you have a force in this quadrant, it's a negative torque. If you have a force in this quadrant, it's a positive torque. So if you're struggling always to remember clockwise, counterclockwise, is it afternoon? Is it 3 o'clock? Like, and you're all confused about what way counterclockwise and clockwise is, just remember quadrants then. And then you should be okay. Draw that on your pivot, remember quadrants, and that might help you remember what pluses and minuses are. All right. So on the table, the boy generates a negative torque, the table generates a positive torque about that pivot. And a lot of people had the signs messed up on those. And that was what they were getting. So just that, if that's another easier way for you to remember pluses and minuses on torques, then I recommend you use that. All right. Any questions about those things? And don't forget you have a test next Friday, right? So, yeah, exciting. It's over 7, 8, 9. All right. Now let's move into collisions. So one of the things that we had mentioned was that we had this impulse momentum theorem. And in it, we said the following thing. In it, we said the following things. That the force average time was equal to the change in momentum of the object. So you apply an external force over some time, you change the momentum of the object. Now what we want to say next is, if F average for the external is equal to 0, then what we realize is that 0 equals delta P, right? That means there's no change in the momentum. Now this is going to be for a system. And so usually I like to think about this as two objects that have the ability, like your system needs to be two objects that can move or should be movable. All right, so if you only have one object that can be kind of moved or directly, if you're applying forces to one object, then that would be this case. But if you have two objects that are movable and interacting, then this is true. Momentum of the system doesn't change. We're not saying momentum of an object doesn't change, but of the system. When we add up all the parts of the system, they won't change. So hopefully we remember the third law. So let's take a look at what we're talking about. So let's say we have two objects interacting. These two objects come in and there's an interaction force between them. Right? So there's interaction between our two objects. Now, when they're interacting, the force between two interacting objects is what? They're equal but opposite directions. Okay. So what we can think about then is let's write up the interaction between our two objects, our red and blue. So the force of the red on blue multiplied by time is equal to the change in the momentum of the blue. Because the red is exerting a force to change the momentum of the blue. Now the other way is the force of the blue on red times time is equal to the change in the momentum of the red object. Is everyone good with that? Now I'm going to use a classic algebra move. I'm going to add up these two equations. So I'm going to have force red on blue time plus force blue on red time equals delta P blue, and I ran out of board space, plus delta P red. These though, one of these is what? Negative the other one because of the third law. So this side adds up to 0. 0 equals delta P blue plus delta P red. So what we see is when two things interact, whatever the change of this one is, this one has the other change. This is where the change goes. All right. So here's my simple little demo for this to kind of drive this home. So how fast is my blue car initially moving? Heard someone say it. It's 0. But notice after the collision, the interaction between the two, the red car had 0 and the blue car has something. So what happens is there's a change in momentum of the red car, but whatever that was goes to the blue car, right? So that way there's no momentum change in the system between the red and blue car. Momentum is a conserved quantity in a system. So notice in my system, red and blue add up to 0. There's no momentum is conserved. Is conserved in the system. Energy is conserved, matter is conserved, momentum is conserved in the system during an interaction. Whatever momentum you have right before the interaction is the same momentum you have after. Notice, we're not saying that the individual object's momentums won't change. What we're saying is that the momentum of the system doesn't change, right? Individual objects can change, the system cannot change. All right. So what you can do next is you can take this equation and say the following. 0 is equal to mass of the blue, velocity of the blue final, minus mass of the blue, velocity of the blue initial. That's the change in momentum of the blue, plus the mass of the red, velocity of the red final minus mass of the red, velocity of the red initial, the change in momentum of the red. Now we can move these two momentums to the other side. So we see M blue, V blue initial, plus M red, V red initial, equals M blue, V blue final, plus MR, VR final. So whatever, this is the momentum of the system before. This is the momentum of the system before the interaction. This equals the momentum of the system after the interaction or the event. Usually for us, this is going to be some kind of collision, but it can be other events as we're going to see. Does everyone follow that? And what would you do if you had a third object? Well, you'd have like plus object 3, plus object 3, right? You can have as many objects as you like. We usually have 2, but you could have a third. I think there might be a homework problem with it. But the idea is that you'll usually have 2. Is everyone okay with this idea? That momentum is conserved. So you can think of the momentum before and after an event. Okay. So this is what I kind of just wrote out. But the idea is that you can have momentum before and after a collision. And the system is going to conserve the momentum so that whatever momentum you have before is equal to the momentum after. And now we're not saying we're always going to get this event. So one of the things that I want to kind of point out real quick, and we'll look at this in a second, every collision is not going to be this, right? Because you can do something like this instead. You could have both objects coming together. You could have this object have more mass than this object. Then the red car continues moving forward. You could have this one have more mass, and then the red car goes the other way. You could have something like this, where both cars are moving forward and this one bumps it from behind. Like there's lots of different scenarios. It's not like it's always going to be, this one is stationary, this one is moving. Like that's one of the many scenarios that you can have in a collision. But what's great is it's always the same equation setup. Momentum before equals momentum after. That's the true statement that always works in a collision or an interaction like that. All right, so what we want to do, wrong way, is we want to talk about like a couple different categories or flavors, if you will. And the idea is that there's two overarching ways of collision, two types of collisions. There's elastic and inelastic. Those are the broad two categories. Now, what distinguishes is something we haven't talked about yet, which is annoying with this. One of the things that this book doesn't do well is you don't have energy yet. But kinetic energy, the energy of motion, if it is conserved during the collision, that is what classifies as your elastic collision. If all the kinetic energy is the same before and after, which means it's a high level of conservation. But when you have that like this, when we have just this, that is actually an elastic collision. All right. Now the other type of collision is the one that usually happens in a lot of cases, and this is called the inelastic. This is when kinetic energy isn't conserved, and an example of this can be this type of collision. Dang it. All right, switch, here we go. So listen for this sound. Did you hear that? When this car hit, that click? That means that's an inelastic collision, because that click is a sound, and a sound takes energy to create. So the energy of the system changed. All the energy is no longer kinetic. Some got drained off to make that sound. Now, another way to think about these is also like if you're in a car, if there's a car accident, when the cars hit each other, they damage the cars. Energy has to be spent to damage or bend up your fender or bump, dent your fender or whatever. Energy gets expended in that, and you don't have all your kinetic energy conserved anymore. All right, so those type of collisions are ones that are inelastic. Now, another type of inelastic collision is this one. When two objects stick together afterwards, right? And they can both, this one can be moving slowly and this one catches up, or you could have them run into each other. Either way, when anything sticks after the collision, those are called perfectly inelastic collisions. So in the most part, there's elastic, inelastic, and then we have that subcategory, perfectly inelastic. All of these, though, have one truth to them, which is we will conserve momentum in all collisions. So the idea that the momentum before is equal to the momentum after for the system, that is true in every single collision. You don't have to worry about the energy if you're going to be able to conserve that. That's like when you're solving these more specialized problems, these higher conservation problems, and you need multiple equations because they don't give you enough information. But for us, we'll be given the information we need for the collisions, right? Because we don't have the kinetic energy piece. All right. So whenever we look at a momentum, what we want to do is the following. We want to identify what objects are in our system. Now, I won't stand here and do that every time and say, okay, our first object is, I'll just start drawing up the picture and putting my objects of interest on the picture. That's what I'll do. Now, establish a coordinate system. I will always use the same coordinate system. To the right is positive, to the left is negative. I'll use that in all of my pictures. I'll define my symbols. So what I'm talking about here is, am I going to call them initial and final, before and after? You can pick whatever you want, but you need to come up with a symbol set that you want to use to track befores and afters. I usually call my objects 1 and 2, and then I use like before and after or initial and final. You should start writing all the information on your picture that you're given. Identify what you're looking for. Write that equation, plug in your numbers, and solve. And if you do it in that order, you have a really high chance of getting the problem right, or getting to the answer that you need. So let's try this. We'll start with a perfectly elastic, a nice, easy collision. So, like I said, I'll start just drawing in my objects, and then I can start labeling all the information. So I have my first object, mass 1. And I'm told that this mass is moving with 3 meters per second this way. So I'll draw 3 meters per second that way. I'm told that there's a mass 2. Now they didn't come out and tell me because I got to add this to the problem. Once and for all. Here. There we go. So mass 2 is initially at rest. So V equals 0 here. Then they tell us this puck collides. So that's my collision. And then afterwards, I'm told that mass 1 is 0. And mass 2 is now moving with some mystery speed. So this will be V2 after. And I'll call this V1 before. Is everyone good? Now I'll establish that my plus is this way and my minus is that way. Then I can come in and say, oh, M1 V1 before plus M2 V2 before equals M1 V1 after plus M2 V2 after. And now I can plug in my stuff and solve. Because I have, oh, I forgot to write this down. M1 is equal to 4, M2 equals 4. And sometimes I'll even write the numbers into the map, into where I put the letters. But I see I have 4 times 3 plus 0 equals 0 plus 4 V2 after. Is everyone good with that? So we get 12 is equal to 4 V2 after, or V2 after is 12 over 4, which is 3. And that's exactly the first collision that I demoed over here, where we see, right? Where we see the one object was initially moving, the other was stationary. There's interaction, the one moves, the other comes to a stop. Is everyone good with that? Now, looking back up over here, I did have this equation written at one point, that delta P blue plus delta P red have to add up to 0. So when we're looking at this, we remember that this is MV final minus MV initial. Well, MV final for the blue, this would then be saying 0 is equal to 0 minus 12, because the blue initially has 12. Now for the red has PR final, P red final minus 0. So we see that the blue gives up 12 units of momentum, and that is how much the red gained, and then we solved for the velocity. But notice that the momentum that one gives up is what the other gains, right? That's what our equation tells us, and that's what we've kind of written out here as well. But this is a little more, I find this to be more systematic in attacking problems. Is everyone good with that? All right, then let's change the problem up just a little bit and see how this changes up. Is it over here? So now we have the same two objects. We have M1, which they tell us, bless you, is 4 kilograms. And it's still moving at 3 meters per second. Now they tell us we have an M2 here, and M2 is a little bit bigger. Do they mention it's at rest? But we need to add that in. So M2 though is going to be at rest. Now, there's the collision event, and after the collision, they tell us M1 is moving, but it has V1 after is 1 meter per second. M2 is moving, so V2 after is question mark, because that is what they're asking us to find based on what we read. Now I'm going to say that this way is positive and this way is negative to establish my coordinates. So I have M1 V1 before plus M2 V2 before equals M1 V1 after plus M2 V2 after. So we write in our equation just like we did last time. Then we can plug in our numbers. So I have 4 times 3 plus 0 equals, now I have 4, but what way do I need to point my V1A? It's supposed to point the other way, because they said it rebounded. So when I plug in the value for V1A, it is negative plus 6 V2A. So I get 12 equals negative 4 plus 6 V2A. So we see that 6 V2A equals 16. Or in this case, V2A equals 16/6, which is about 2.7. Should be close. Is everyone okay with that? Now, again, if we're thinking about this in terms of our delta P blue and a delta P red, notice delta P blue is 16. So delta P blue, it gives up 16 units of momentum that gets transferred into the red. All right, and then that means that because the red is bigger, it's moving a little slower because it has more mass. Is everyone good with that? And that's exactly this scenario where this is stationary, and notice the blue car bounces back a little bit versus the red car which goes forwards. Is everyone all right? And this is actually an elastic collision as well. That's an elastic collision. All right. Now I want to look at another, we're going to look at another collision. All right. So in this collision, this is a special category of collision. These are called recoil events. And these are kind of interesting because in a recoil event, the initial momentum is 0. All right. So let's look at the recoil event. So a recoil event looks something like this. When we're talking about recoil, it's something like this. So initially, before I push the button, the system velocity is 0. Then after the event, the cars move away from each other, but they will move away in such a fashion that the change in the momentum is 0. So you had 0 momentum before, you have 0 total momentum after. The classic example of this is shooting a gun. All right, so if you've ever shot a gun, when you pull the trigger, the gun kicks back some, right? And it's worse like in a shotgun than it is like in a handgun. Now, if you have a really big handgun, it will really kick back. Now, the one that I always joke about is this is one of the reasons you can mock Hollywood as much as you like, because like they have seen movies like Rambo where he's holding a 50 caliber machine gun in an arm and it's shooting and the gun isn't moving. In real life, a 50 caliber machine gun is mounted on a tripod and it takes a team of 2 to 3 soldiers to move and operate that weapon, not one guy holding it in his arm. Right? So that's, if you ever watch it, it's pretty fun. But this is also true in a lot of movies. They show the guy pulling a trigger and the gun is just stationary. No, the gun will have kickback, right? So the idea is that you have to, it's just one of those things. But it's also how spacecraft fly. Most of our spacecraft, they're kicking out exhaust this way and the ship moves the other way, right? That's the same idea. So we're going to look at a different problem related to this. And our problem is going to be someone jumping straight up in the air. All right. Now, when someone jumps straight up into the air, at their point of highest jump, what is their velocity in the y? 0. And if you jump straight up, what is your velocity in the x? 0. Now, if you're holding a ball, what is the velocity of the ball? 0. So we'll say VB is 0 for the ball. Now there's an event. And after the event, The ball is now moving, they say at 10 meters per second. And they say, what is the velocity of the person after? That's what we're trying to figure out. So they do tell us that the mass of the person is 40 kilograms and 50. The person has a mass of 50 kilograms and the mass of the ball is 1 kilogram. So we need to figure this out. So we write up our equation. Oh, we'll count this way positive, this way negative. So we have mass of the person, velocity of the person before, plus mass of the ball, velocity of the ball before, equals mass of the person, velocity of the person after, plus mass of the ball, velocity of the ball after. So we have 0 plus 0 equals 50 velocity of the person after plus 1 times 10. So we see that 0 equals 50 velocity of the person after plus 10. Subtract this over, divide by 50. You get negative 10 over 50, which is negative 0.2 per second. So we're not saying the person's flying backwards with some great speed, but the person will, if they jump up and throw the ball, they'll land a little bit behind where they jumped up, right? And you can actually see that in basketball. Like if you watch, sometimes the guys will run up, they'll stop it, like they'll come to a stop, jump and shoot. And then if they land, they usually land a little bit behind where they jump. So you can try it out and see. You have good vertical skills, you jump up, throw the ball, and land behind. But this is the idea. When you push off, something has to go the other way. This also comes up like they have things like fireworks are launched into the air and explode. The one fragment goes one way, the other goes. But that's the idea of explosions follow this principle. Right. Any questions about recoil? No. Okay. Then I completely have to come. Oh, gotta record the problem a little bit. So while we're doing that, letting the problem sit there for a second, we're going to skip that for a moment, and we're going to talk about inelastic collisions for just a moment. Then we'll come back to the last problem. So we said that there's this category of perfectly inelastic collisions, and this is whenever two things come together and stick or become attached in some way. And so when you see this, we still have our same type of system where you have like M1 V1 before plus M2 V2 before. Now we can say that this is M1 V1 after plus M2 V2 after. So we can say that because that's our true momentum conservation. But when we look at the collision, we have to think about this. We have our system. Oh, start it again. When we have our system, what speed do they have? How does the red and blue speed compare after our collision? Are they different or same? They're the same, right? Because they're moving together. They move as one unit. So what we see then is that V1 after is equal to V2 after. So we have M1 V1 before plus M2 V2 before is equal to, we can factor that out, and call it M1, M2, V after, because they're the same. Does everyone follow that logic? Right? And so these are always great because you're like, oh, I can do this. It's got like less variables and stuff. All right. Is everyone okay with this idea for this? Cool. So anytime something comes together and sticks or connects or becomes one unit, that is what we will do. And notice it's the same thing over, it's the same equation over and over again. All right. So we're going to do this problem. We're going to have this person jump on a skateboard. So initially we have some person, and this person is running, they say at 5 miles per hour. And then there's this stationary skate. And so that means this velocity is 0. Then there's the event. The person jumps on the skateboard. After the event, they're moving together with some VA that we do not know. Now they do tell us the mass of the person. The mass of the person is 40, and the mass of the board is 1. Is everyone good with that? So then we can come down here, write our equation, M1 V1 before plus M2 V2 before equals M1 plus M2 V after. So once we have this, we only have one thing left to do, which is what?
Like plug in the numbers.
We'll plug in the numbers, but can I plug 5 miles per hour in? No, so we have to convert that. So we say that V1 before is 5 miles per hour. And what's our conversion from miles per hour to meters per second? 4 nines. And that's because we remember that there's 1,600 meters in a mile, and then there's 3,600 seconds in an hour. And that gets us our 4 nines. And this is yeah, 2.2 meters per second. So now we can come back here and we have our 40 times 2.2 plus 0 equals 40 plus 1 VA. And so we see that this side is 88 and that equals 41 V after. So our V after is 88 over 41. And it should be just under 2.2, so 2.17. So usually your final velocity in a problem like this will always be smaller than one of the initial velocities because you have a combined mass in the system. All right, so usually you'll slow down. Also, as a fun question, if the mass of the skateboard was 2, would the final velocity be smaller or bigger than this? So if you change this number to 2 instead of 1, VA is smaller or bigger than that? Smaller, because as this number gets bigger over here, this number gets smaller over here. You have to distribute that same momentum over more mass, decreasing the velocity. Is everyone good with that idea? All right, then we'll go back to this video. So the story behind this is someone shared this video with me and they wrote down the physics of this video. And I found it so entertaining that I now use it as an example. So let's watch this video. Someone said this one here. The what?
Grown-ups.
Grown-ups too, yeah. All right, so let's take a look. So this is the numbers that they pulled out of the video. And they had to look some of these up as well online. But Shaq, you can find his average mass or whatever that they claim he is at the time. They found the mass of the person in the tire. I think that was David Spade. I think is what they said. So you can look up his mass. They looked at the brand, that type of tire online and got an average tire mass for that type of tire. Now the speeds. So it turns out, if you don't know, these are the fun things you learn along the way. Intersections have standard dimensions. And so you can measure, you know the dimension of the intersection, you can calculate the speed of the tire, kind of coming in and out. And then they use the number of revolutions of the tire kind of bouncing away versus the amount of time it took to spin the tire to get the speed coming off. All right. So, if you start parsing out the information, you can get to some numbers. Now, of course, this is just for fun, but the idea is still the same, that Shaq should probably move. All right, that's what we're going to find out. All right, Shaq probably wouldn't be able to stand there and get his tire. But it is for entertainment, and he is Shaq, so it's possible. Let's take a look. So we're gonna say that we have some tire. And our tire is moving at 2.85 meters per second. And then we have Shaq. And so this tire is going to end up hitting Shaq. So that's an event. And afterwards, they tell us the tire goes back the other way at 2.85 meters per second. And here is Shaq. So we're just going to call this velocity Shaq. And there should be something there. And we can call this velocity before, velocity after for the tire. We know the mass of the tire with the person in it is 396. And the mass of Shaq is 147. And now we repeat the same problem. We have mass of the tire, velocity before, plus mass of Shaq, velocity of Shaq before, equals mass of the tire, velocity of the tire after, plus mass of Shaq, velocity of Shaq, right? We apply our same equation to this problem. So we plug in a bunch of numbers. What's 396 times 2.85? What's just this?
1,128.6.
That's fine. And this is then equal to minus 1,128 plus 147 velocity Shaq. Okay? So notice that we're going to add this over. This is 2256 is 147 velocity Shaq. This 2,256, that is the change in momentum of the tire. We're going to come back to this in just a second. Now, divide the velocity of Shaq, and Shaq then should have moved with the speed of 15.3. Now we can call this an upper bound, but Shaq should have moved with something. He shouldn't have been stationary. He should have at least stepped back or something from that hit. So now what we can think about is saying, okay, we'll give Shaq the benefit of the doubt. All right. And what we can think about then is the force average times the time is the change in momentum. So the Shaq here has to apply a force to the tire to give the tire that impulse. So what is the force between Shaq and the tire during this interaction? So you can time the amount of time it takes for the tire to hit Shaq and bounce off. It's about 100 milliseconds. All right. So the force between Shaq and the tire times 0.100, we just said was 2256. And so the average force between Shaq and the tire is 22,560 newtons. That's a big force, right? So the idea is that probably Shaq should have moved. Now you could have said, here's the other part. You could say, okay. Well, what about friction forces? That's what would have stopped him from moving. That's fine. And then you find out like he has like some high coefficient friction shoes or something. Some unrealistically high coefficient shoes. Plus then you can start also looking at, well, maybe he should have bent a little. It's like rigid. So you must have like incredible core strength to take that tire as well. Right. But the whole point is it's a silly scene, but you can apply physics to things just to prove how silly they are. But it's a fun way to look at using impulse and momentum. The other one that's really great is when people get shot and then they fly back like 6 feet. I was like, no, like a little 9mm bullet doesn't have that kind of momentum. But that's all we're gonna look at today. So I'll see you on Monday. We're gonna apply this same principle to rotating systems on Monday. All right, we'll look at angular momentum conservation. So we'll do the same thing but for rotating. If you have any questions, you can either send them through emails or have a good weekend. See you later.